Hi everyone, my name is Charmi Patel and I'm a second year grad student in the physics department. Today I want to talk to you about ultraviolet airglow intensities as seen from lights. That's a lot of words, so let's get right into it. We want to measure airglow. Well, what is airglow? It is the glow of the planet if you're outside looking in as shown as the picture. Why is the planet glowing, you ask? During the day, the energy of the sun's rays ionize the molecules that are present in the atmosphere, and at night, the same ions recombine to form molecules. All these processes emit light at signature wavelengths. We can use this information to find what particles are present and their densities. Okay, so why do we care? The simple answer is that all communication devices that you use, such as the GPS, phones, etc., all rely on radio wavelength signals that travel through the atmosphere and bounce off of it. Bad news is that the atmosphere has the ability to absorb, emit, or modify these signals. So really, the changes in the ionosphere lead to disruptions in the signals and bad functioning of the satellites that are in the ionosphere, which is why we need to monitor the ionosphere, and the way to do it is by measuring airglow. The instrument used to measure airglow is the limb imaging ionospheric and thermospheric extreme-ultraviolet spectrograph, or lights for short. It measures in the UV, and it was part of the STPH-5 platform on the International Space Station. It was launched on February 19, 2017 and took about 9 months of data. So what does it mean to take data? Well, light faces the trailing limb of the ISS. The light enters through the instrument, first passes through the baffled slit assembly, which keeps the particles out and lets the right light in. Then the light hits the toroidal grating, which takes a vertical column of light and disperses it to make a horizontal spectrum. The spectrum is projected onto a 2D MCP detector area to store and send to Earth. The main objective of this project is to identify trends in intensity with respect to latitude, local time, and geomagnetic conditions. On the top right is a GIF of the lights data. Lights collected the spectrum of the ionosphere and sent it back to NASA every 3 seconds, and it did that for about 9 months. I'm focusing on the 5 features that are mentioned here. To get the brightness of each line, I summed over the vertical axis of the image, then performed a Gaussian fit. You can see the original image of the line on the top right, and then the fit on the bottom right, with the data and fit sitting right on top of each other. The orange line represents the background. I did the fit for 834 angstroms, and here is the result. All 3 plots have time on the x-axis in days since January 1st, 2017, and y-axis is apparent solar time under the ISS in 24 hours. Each vertical line represents 1 orbit. Each orbit sees all 24 hours. Therefore, you can see that the top plot shows 834 intensity starting out dim at the bottom of the graph, getting brighter as we move to the middle, and then dimming out again at the top. Similarly, the middle plot shows the background of that 834 line. Its variation scales as intensity does. The circled spot that is missing is probably the location of the sun, where the instrument was consistently turning off and then on again when the sun was in direct view. The bottom panel is the AP magnetic index to see how the magnetic activity affects the spectrum. The goal for the project is to make similar plots for all the lines mentioned above and identify trends that can be useful for other ionosphere-based projects. That's all I have for you today. Thank you for listening.